So, welcome everyone to the One World Combinatorics on Words seminar. We have two speakers today, Leo Poirier and Wolfgang Steiner. They're going to speak about factor-balanced S-adic languages, and I believe Leo will start.
Yes, thank you. So yeah, this is a presentation on a joint work with Wolfgang, Wolfgang Steiner of IRIF and myself that we did during my internship, my research internship last summer. And so it is talking, as you said, about the factor balancedness of S-adic languages. So we place ourselves in the classical framework of a finite alphabet and a language over that finite alphabet, that is to say, a set of words, of finite words, upon that alphabet. Then the notion that we're going to mainly focus on is the notion of balancedness, which declines in several definitions that I will first list to make sure that we are clear with the definitions. So first, the most basic and fundamental definition that we could have with balancedness is being, for language, to be C-balanced with relation to a certain factor V in A star. So if you take, given a factor V in A star, and two words of the same length in the language L, being C-balanced with relation to that factor V means that the difference in the number of occurrences of V in those two words W and W prime, which we will note as you see here, as the length in V of those words, this difference would be bounded by some constant C that needs to be independent from the length of W and W prime. But it is important to notice that it can be depending on the length of V, or even depending on V. But sometimes you will see that we will omit this constant C, as the question that we'll mainly focusing on is the existence of some constant, the fact of being balanced with relation to a certain factor V. And so this is called balancedness, in more generally, balancedness and not C-balancedness. If you need to go a bit stronger, like for example being C-balanced for all V of some length n, then you will call it balancedness for length n. And if n takes specific values, especially if L is equal to 1 and n is equal to 1, then we call it, and that's the usual notion that has been mostly studied, which is called letter balancedness. But then if it is balanced for all n superior or equal to 1, then we call it factor balance. And the reason why we call it factor balance is because, well, it is really equivalent to being balanced with relation to all V in A star, but if V is not a factor of the language L, then the property is kind of trivial, because the length in V, the number of occurrences of V, is equal to 0. So we only have to check really the factors of L. To get a bit of understanding of what has been done before, the study of balancedness takes us back at least to the 1940s, where Morse and Hedlund showed that the language of a Sturmian word is letter 1 balanced. So that is to say that if you take two words from a language of a Sturmian word, and those words are the same length, then for any letter A, the number of occurrences of A in those two words will differ at most of 1. And more recently, in 2002, Fagnon and Vuillon showed that the language of a Sturmian word is factor balanced. And more precisely, the bound for a given factor V is length of V. And one stronger result, as we say earlier, is that to be factor C balanced, so to have a constant C to be independent from V, to have such a constant, you need to have the slope of that Sturmian word to have bounded partial quotients. But if the property was verified upon all languages, it was equivalent to be letter balanced and factor balanced for every languages, it would have no interest to study it. So here is an example of a word, of a language. So the language of a Tumors word, which is letter 2 balanced. This can be seen really easily, as you see below. Like if the length of any word from this language is odd, then you have only two possibilities between the repartition of the two letters, either n and n plus 1 or n plus 1 and n. And if the word is of even length, then the repartition is either n, n-1, n+1, or n+1 and -1. And hence you see that the biggest gap you can have between the two could be at most 2. So the language of the two-or-more word is letter 2 balanced, but this has been shown really recently by Berthet and Checky Bernales. The language of the two-or-more word is not balanced for length 2, and therefore it is not balanced for length greater than 2. And so the study of factor balancedness has been a bit more elaborated. For example, when we started to work, we had one property for the equivalence between letter balancedness and factor balancedness for S-adic languages, that is to say languages generated by a sequence of morphisms, which is if the sequence contains only left or right proper unimodular morphisms, then factor balancedness is equivalent to letter balancedness. And this is why what we tried to kind of study, this corresponding between letter balancedness and factor balancedness. So first, I will present to you the results we have had on the effects that applying a morphism to a language has on the balancedness properties, and then Wolfgang will present to you the extension of it to S-adic languages. So first, the one property that is important to be reminded is the characterization of being letter balanced with the distance, the bound with the distance from a certain vector, which is called the frequency vector. So this has first been studied a bit by Berthet and Tillman in 2002, and then proved by Adamczewski. So you have it both ways. So if there is a frequency vector such that the distance between this word, the number of occurrences in this word, and the frequency times the length of this word is bounded by C, then the language, and if this property is obviously verified for all W and all A, then the language is letter 2 balanced. And the reverse, if the language L is an infinite letter balanced letter C balanced factorial language, and by factorial language we mean, and that will be the definition that will imply every time, like we use as we study factors of a language and factors of words of a language, we assume that this language is stable by taking the factors of it, so it contains all of its factor. That's what we call factorial languages. And so if a factorial language is letter balanced, then we have the existence of such a frequency vector. The other property the other notion that we will use during our demonstration is the notion of encoding of a word. So if you take a word A1, A2 to the A big N, so of length big N, you can define the encoding of that word as taking the successive chunks of length n of that word, of length small n. And so the important notion to remain is that those chunks are overlapping each other. You don't take A to A1 to AN and then AN+1 to A2N. You take A1 AN and A2 AN+1, etc. And obviously, if we will kind of to be more rigorous, if big N is smaller than small n, we will say that the encoding of that word is, well, the empty word. The important the point of that notion of encoding is that if you take a factor v, a word v, and a factor v, and you want to know the number of occurrences in that word, if the n is the length of that factor v, then it is the same as looking at the number of occurrences at v in the encoding of w. And in that second formula, you have that, so in here, v is considered as a letter now of the alphabet A to the N. And therefore, you have the equivalence between being balanced for length n for a certain language L and being letter balanced on the new alphabet A to the N for the language of the encodings of the words of L. So first property of preservation of balancedness would be if you have a language L that is letter balanced and is a factorial language, and a morphism sigma then the factors of sigma over L is also a language that is letter balanced. This property can be shown by cutting the images of sigma in a certain way, because at first the idea that you want to use when you have images from sigma is to kind of cut them in chunks of images of each letter of a word from L. But the point is that if you take factors of sigma of L, you don't always end up exactly on those chunks. And so you have to, well, identify the biggest chunk that you can take in common. And that is what we show here. It's like there exists a cutting of both W and W prime, so that they have a central chunk called Y and Y prime of the same length, on which we will be able to apply the letter balancedness in L. And then the prefix and suffixes are of bounded length, and those bounds are independent in the length of W and W prime. And that is the main idea, because if it is independent, then the massive constant that we will have by counting the occurrences, for example, of a certain letter B in W will be bounded by the same constant. And so to detail a bit what happens for the passage as far as Y and Y prime are concerned, the number of occurrences in Y, in sigma of Y of a letter B is the same as the sum over all the letters of the first alphabet A of the number of occurrences of A in Y times the number of occurrences of B in the image of A. And so this sum is roughly, this is a kind of a rough bound, but as long as it's independent from the length of W, well, it's enough to affirm that it is letter balanced. And then you have the reverse property. So if you have a language L that is a factorial language and a substitution sigma morphism, for between two alphabets, the fact of F of sigma of L to be letter balanced is equivalent to L being letter balanced, as long as sigma has its incidence matrix being invertible. And the proof roughly only uses the proposition 1, so the frequency vector, because when you have this frequency vector, the visualization that you want to have is kind of a geometric point of view, where you have a directive line directed by this frequency vector, and those words are in a certain strip around that director line. And so if they are contained in a strip in F of sigma of L, applying only an invertible matrix, which is M sigma minus 1 to that line and to that strip, will remain the image strip in L to be also bounded. And so that's how you get the reverse side. But you need to have sigma to be invertible. Then to study the property for N, for balancedness in length N, you need a stronger assumption over sigma. You need sigma to be what is called proper. And so the property is like, if you have a factorial language that is balanced for length N and sigma morphism, and we say that more generally than only being proper, we can assume that there is a certain factor U that is the same, for example, let's say the same prefix of any images of any letter. So you know that the prefix or the suffix is independent from the letter. Then you will have you will be transmitting some of the balancedness, and the length up to which you are transmitting it is given by this constant, which is kind of ugly. But when you take classical property for morphisms, for example, sigma being non-erasing, then you have that F sigma of L is balanced for length N. And if you furthermore assume that sigma is left or right proper, that is having the same first letter, for example, or last letter, then you have the balancedness for length N plus 1. And that will be really useful to show it, to show the balancedness for any length greater than 1. So the proof, first, let's start with a specific case, with the case of being L being 1, so being letter balanced. And we want to show that if sigma is proper, then F sigma of L will be balanced for length 2. And so the problem with, and so for that, we will use the 2 codings of words, of the images of those words. But the problem is, if you look at the last letter of sigma of W1, the chunk of size 2 overlaps the beginning of sigma W2. And so if you don't know what sigma of W2 and more generally the next chunk starts with, if you don't know what it starts with, then you have some dependency between the 2 coding and the image of the next letter. And so you cannot define a proper morphism upon letters that you extend then to words and to infinite words. But if we suppose that sigma is proper, then we have independence between the letter and the starting of each image of a letter. And so you can define properly what we do here with sigma hat, the substitution that associates a letter W to the 2 coding, or more generally the encoding of the image of that particular word. And so more generally, this property can be expressed by this constant, which really means that you require M. So the M is to remind you, M is the bound at which at most it is balanced for length M. And so if you take M to be smaller than this minimum, which is to have, which really means to have at least n minus 1 bit, n minus 1 letters on that chunk, then in the length of U, which kind of allows you to overlap on the next, then you will have, by the same way, this sigma hat generalized to the length M to be defined as a proper morphism upon letters. And so you have using the properties on letter balancedness and appliance of a singular morphism, you have the preservation of being balanced for that length M. And so to preserve factor balancedness, which is to be factor balanced for any length, to be balanced for any length n greater than 1, you have that if L is factor balanced in a factorial language and sigma substitution, or morphism, sorry. So the difference between the two that I'm mixing is if you have a morphism between the same alphabet, A star to A star, we call it a substitution, and then more generally it's called a morphism. And so if you have a substitution and a factor balanced language, then F of sigma of L is also factor balanced. So for non-erasing morphism, this is a direct corollary of the proposition that we've seen before. And with morphisms that can sometimes erase letters, we showed it by using what we've seen before and the characterization of balancedness linked to the distance to that frequency vector. So I think it's Wolfgang's part, so I will stop my share and let Wolfgang share his part.
Okay, so let me continue now on aesthetic languages, so which was the title of the talk, was factor balancedness for aesthetic languages. So those are defined by sequences of morphisms, sigma k, and so we denote by sigma kn the composition of morphism sigma k to sigma n minus 1. And then the language of the sequence of morphisms is the set of words in A0 star that are factors of images of letters by sigma 0 n. So you could take this just for the union over all n, but it's slightly better to take infinitely many n. So it makes only a difference when there are some substitutions sigma k where not all letters of ak appear in the image of ak plus 1. So you usually could just think of the union over those sets. Now we don't only need language L sigma, so at level 0, but we will consider that all levels k, so we replace the 0 here by a k, and we start from sigma k. So this case has nothing to do with the k codings from before, sorry for that. But note, so the important property here is that L sigma k is related to L sigma n by this relation. So it's the image by sigma k n and then taking all factors. And so we also need a definition for properness for sequence of morphisms. So it just means that for any k, they have an n larger than k, that sigma k n is proper, so left proper, right proper. And the last notion we need is the notion of everywhere growing. It means that the lengths of the images of letters tend to infinity as k tends to infinity. So now we can state the main theorem. It tells us that if sigma is left or right proper, and all the languages L sigma k are letter balanced, so for infinitely many k or for all k it's the same, then the language L sigma is very factor balanced, aesthetic language. So what's the idea here? So just that, so we, as Leo said, that if we have a proper morphism, then we go from balancedness of length n to balancedness of length n plus 1. And since we have infinitely many proper morphisms, we attain all, from length 1, we attain all lengths. So this is a generalization of the result by Perdet, Jacqui, Durand, Leroy, Perrin, and Petit, who assumed unimodularity of the morphisms. So, okay, we can, if the incidence matrices are invertible, then it's sufficient to look at L sigma, the letter balancedness of L sigma, because this implies letter balancedness of all L sigma k. And if we don't have properness, then we need balancedness for length 2 for infinitely many k, and we everywhere growing has to be factor balanced. Because, for example, as we've seen for the 2 Morse substitution, it's letter balanced, but not balanced for length 2. So if we consider the special case where we have a constant sequence of morphisms, so all sigma k are equal to some sigma, then our result just tells us that if sigma to the k is left or right proper for some k, and the language, the substitutive language is letter balanced, then it's also factor balanced. And if we don't have properness, then we need balanced length for length 2 to have factor balancedness. So this was somehow known. So it's, for example, in the book of Kefelec and the papers by Adamczewski, they've established a relation between sigma and so they have defined a substitution sigma n that work on this n codings, and they have shown that all these sigma n, they have the same eigenvalues except for eigenvalue 0 starting from n equals 2. So there's a difference between n equals 1 and n equals 2, but starting from n equals 2, we have for all lengths, they have basically have the same properties. And now we have this, but I think this property is not explicitly stated. So now we have that balancedness for length 2 is enough to have factor balancedness. It's nice. So here's a particular class of aesthetic languages, which was in fact the motivation for at the beginning for studying this topic. It's what I called 2 Morse Sturmian languages, because we have 3 morphisms, L, M, and R. L and R are Sturmian ones, and M is the 2 Morse substitution. So that L, M gives us, of course, the 2 Morse word, and this L and R gives the Sturmian word. Now we know that, okay, the 2 Morse word is letter 2 balanced, so it's 2 balanced for letters, and Sturmian words are, of course, 1 balanced. And if we mix them, LM and R, then we still remain two balanced for letters, but of course not for factors, because we already know that the 2MOS word is not factor balanced. And now we have in a concrete characterization. So a word, so for a given sequence sigma of LM and R's, L sigma is factor balanced if and only infinitely many sigma k's are different from M. So I will give the proof in a moment. Before that, let's just mention that these kind of languages, they give examples where we have balancedness for certain lengths, and not balancedness for some larger lengths. So this balancedness for these lengths, it was just a consequence of this substitute of proposition 4, where we just put this length here, and if we and this not balancedness will show this in the proof. So let's first assume that infinitely many sigma k are different from M, so they're equal to L and R. So L and R, you see that they are both right proper. So this gives a right proper sequence of morphisms, and we have seen that okay, all languages are letter balanced. So our theorem tells us that the L sigma is factor balanced. Now for the other direction, suppose that almost all sigma k are equal to M. So this means we are in this situation that we have LM, so the fixed point of M, then apply a substitution sigma, which is a concatenation of LM and R's, and then take the factors. So so Berthet and Jackie, they showed that LM is not balanced with respect to factors of length 2. So for example, for factor 1, 1, this is 2 because this has frequency 1/6, and 6 doesn't divide the length of M to the n of 1 for all n. So more precisely, Berthet and Jackie, they have a statement that says that if you have a substitution sigma and a factor AA, which has a rational frequency, then the denominator of this frequency must divide sigma to the n of A for all n that are large enough if we want the L sigma to be balanced with respect to this factor AA. And since this is not true here, then it's not balanced with it's not balanced. Of course, for the 2MOS word, we could also just construct words that violate the balancedness condition. So, for example, if we take a sequence of words UN and UN prime, that where U1 is 0, 0, U1 prime is 0, 1, and then for even n, we define the UN and UN prime like this, and for odd and like that. Then it's not difficult to calculate the difference between the number of occurrences of factors of length 2 in U2n and U2n prime, and then we see it's equal to n, so it's unbounded. And all these words are in the language of 2MOS world. So now we know that LM is not balanced for length 2. And now to extend to sigma to LM, we need a small lemma that tells us that, so if we consider this word sigma of 0, 1, 1, then it occurs in sigma of W only trivially. Trivial means that we only have to look at the occurrences of 0, 1, 1 in W and to take images of it. It cannot occur as somewhere as an overlap. And so this gives, so that if we take the difference of the occurrences of factors of sigma 1, 1 and U2n and U2n prime of sigma of U2 and U2n prime. It's the same as taking occurrences here. And since the 2-Morse language, of course, doesn't contain 1, 1, 1, it's the same as counting 1 1s, except perhaps there's only a small difference at the beginning. And so we get that this difference is n-1, so it's unbounded. So this proves that also all these languages, they are not factor balanced. And this proves our theorem. So this talk was mostly about the relations between letter balancedness and factor balancedness. So let me just say some words about letter balancedness. So we have seen at the beginning in proposition 1 that we need a frequency vector. So for acidic sequences, this means that this intersection of nested cones, they tend to align. And moreover, we need something stronger. We need that all Poirier vectors of words must be in bounded distance to the line. In particular, we need that this the Poirier vectors of sigma 0 and b are in a bounded distance from the line. But this is not always sufficient. So, for example, Cassin, Ferenczi, Zamboni constructed Anu-Rossi words that are unbalanced for letters. But yeah, I think that all Anu-Rossi words, this is satisfied. But then if you could make a more refined analysis, then you find words where you are arbitrarily far away. So there are also other papers on Anu-Rossi words and balancedness. And yeah, papers for Brun words, which are use similar techniques as Cassin, Ferenczi, Zamboni, and for Cassin words. Okay, so yes, I haven't prepared a slide for open questions, but I just wanted to mention one question. This was about this factor C balancedness. So for factor balancedness, we assume that C can depend on V, on the word V, and so factor balancedness is not the same as factor C balancedness for some C. And we know from Van Yo and Vuillon that certain Sturman words are factor C balanced. But I think that we don't know any other words that where this C is an absolute constant. Yeah, it would be interesting to know if there are other words. Yes, and this was basically all I wanted to say. Thank you for your attention.
Oh, thank you very much, Wolfgang and Leo. Does anyone have any questions?
Can I have a question?
Yes, please.
So I'm sorry if I'm wrong, but you give sufficient computation for C balanced for certain acidic.
Sufficient. Sufficient. It's what difficult.
So you've given
no, sorry. Yes, it's important. No, sorry. Yes, if you have a convergence here, so if they're not only this distance is bounded, but if you have exponential convergence to the line in n, this is usually sufficient. So
Okay, thank you.
Yes, if I have a finite set of for example, of morphisms and the exponential convergence of this is sufficient. So like something like the second Lyapunov exponent is negative, then this is a sufficient condition for balancedness.
Okay, thank you. I'm sorry for my bad understanding.
Dan, you have a question?
Yeah. Hi, Wolfgang and Leo. Very, very nice talk. Thank you. I was wondering, all of these different notions of balancedness, which of them are preserved under topological conjugacy? Because I guess not all of them are, right?
So you're speaking about those. I have not thought about this. Yeah, sorry, I don't know.
Yeah, if not, that's
I
fine.
don't know.
But like, for instance, I guess letter balanced isn't preserved, right? Because you could start with something which isn't, and then just make all the zeros and ones the same frequency or something, and that would preserve it. So I guess some of them are, and some of them aren't.
Yeah, certainly, yes.
Okay, no worries. Thanks.
Yeah, so.
Marie-Pierre, did you have a question?
Yes, I have two questions. First of all, I missed the beginning of the talk. So the first question is the talk explained the properties of conservation of balancedness through a morphism. Are there links with recognizability properties?
No, I don't think so. Except that it works for all morphisms, and both properties are true for all morphisms. So yes, if letter balancedness is preserved by all morphisms,
Yeah.
and vector balancedness is preserved by all morphisms. This is.
You don't use any recognizability property for the proofs. Okay. So the second question is a minor question. So in the definition of the language associated to adic shift, you say that you keep the words factors of images of sigma 0n for infinitely many n. And if you remove the infinitely many n, does it change a lot of things, or it is
a lot of things, but it changes this relation a little bit, and this was a very useful relation. So yeah, well, I don't know. You also have to be careful a little bit. But of course, you can just assume from the beginning that all the sigma k's are defined in a way that all letters of AK appear in the images, because otherwise you just remove the letters that don't appear in AK, that don't appear in the images.
So you remove some unuseful words.
Yes, otherwise, if infinitely many n is not the same as for some n, then it just means that you have some letters in some alphabet AK that are useless. So you can.
Okay. Thank you.
Benjamin, question?
Yes, bonjour Wolfgang, bonjour Leo, merci pour l'exposé. So my question was, when I saw your slides with the frequency vector, I wondered if being factor balanced had anything to do with having a unique shift invariant probability measure. Yeah, do you know anything about that?
Yeah, well,
Like
for
the frequency vector
languages, this is true, yes. So it is, in fact, the balancedness implies a unique
right.
shift and measure. So is this well, well, in general, of course, you could take two words that have they have the same frequency, but they're not in the same shift, and I think it's you could construct measures that the two different measures. No?
Oh.
So since we are really studying only languages, because so balancedness is a property of languages. Usually one studies balancedness on languages coming from shifts, but so no, I think you can take two words that both stay in the same bounded distance from the line, and
when you take the closure, like because you have probability measure, don't you get the same orbit? If I'm
not sure. Yes,
I don't.
Yes, let's think about it.
Okay, thanks for that.
Does anyone else have any questions? If not, thank you again, Wolfgang and Leo, for speaking in the seminar. We have, I think, a bit